thought you'd lie. I'm sorry, I didn't notice that. Okay, starting 20 seconds early since we're all here and all, just to make sure people are aware of things on Moodle. If you want to go and look at your graded homework, you just come down here right below the lecture slides, right? These are the slides that were used for presentations in class. And in case you missed it, this here is the link to watch the video. Yeah, watch the lectures.
I don't think any of ours have.
Actually, you're right. They're only half graded. Well, when they're graded, you would just click here. And if you click here now, instead of showing you the questions, it's going to show you the questions with solutions to them. So you can read the solutions here. And then you'll have a place here where there's a feedback file when it's graded. And I forgot it's not graded yet. He was working on them yesterday, but didn't get to them.
The last one we were supposed to put an equation. Like if we explained it.
Yeah, you just need an explanation to explain why.
Oh,
yeah.
Okay. I was
yeah,
like,
mine.
I didn't write like the equation for it.
Mine have, a lot of work, and you very well may have less work. So that's where you have that. If you want to review your potential test questions, you can just go down here to PTQ1. You can click there. You can see your score, it's 1 to 5 on each thing. So you can see what the score breakdown was. And you can see if there's that little red thing in the corner to tell you if yours would likely be used. And of course, you also have them out in the boxes out here. So I just want to make sure people, know where these things are. And if you want to check your grade, of course, you click here on grades. I won't do that because it would show you everybody's grade, and that's not appropriate. So we should get it, or actually we just started momentum on Wednesday. And so today, the big snow day that was supposed to have 8 inches and now might have 2 of snow, we'll get into momentum. So last class period, we learned that momentum is mass times velocity. It's a vector. What does it mean if I say momentum is a vector?
What is the direction?
It has a direction. That's right. It has a direction. So my example from class on Wednesday was, the Chiefs and the Patriots have a forward momentum, a winning momentum, if you want to be accurate. The Raiders have the opposite. They have momentum, but it's in the opposite direction. Yes.
Why do we use P for momentum?
I don't know. That is a very good question, and I don't know.
Okay. Because I already know that there's mass, so you can't use in, but
It could be Latin or something, but I simply don't know. Now, Grace.
So whenever describing momentum, we have to also state the direction.
Well, just like when we have the word velocity, we know that means with direction, speed without. But everything else like acceleration, we'll sometimes talk about the vector acceleration, sometimes talk about the scalar acceleration.
Oh.
So it depends on the context.
So sometimes it's a vector, but not always.
Well, momentum is a vector, but when you're working with it, sometimes you're working only with the amount in this direction, what we call a component. And so that's the difference there. So momentum, what should the units be for momentum? P is the symbol.
maybe it stands for product.
I don't think so.
The product of mass and gravity.
Yeah,
Mass and velocity.
but
sorry.
force is the product of mass and acceleration.
Yeah.
What should the units be of momentum? What?
Can you repeat the question?
Well, what should the units of momentum be? Okay, so it had units. I first heard it from Hosanna. I hear other people saying it should have units of mass times velocity. What are the units of mass? Mass.
Kilograms?
And then, now Hosanna, the units for speed or velocity.
Seconds.
what you had said earlier.
Oh, meters per second squared.
So the units for momentum are kilogram meters per second. Kilogram meter per second is the unit for momentum. So if I have an object with a mass of, here's an object, and it has a mass of, let's say, 2.5 kilograms, and it has a speed, so now I'm talking about the scalar, a speed of 3.0 meters per second. What is the momentum of this object? I got an answer, so I'm going on. 2.5 times 3 is 7.5. I know my kilogram looks like a hieroglyph. There. So that's the way you calculate momentum. Of course, so far we've seen nothing useful in momentum. We've just seen, hey, look, it exists. So a simple question for you, much like what you had in lab yesterday, if the speed of an object is doubled, then what happens to the momentum? That, since it doesn't mention it, that's assuming the mass of the object stays the same. So if the mass stays the same and the speed is doubled, what happens to the momentum? It doubles. Now, it's trivial, right? But when we learn about kinetic energy, we'll learn that kinetic energy is proportional to the speed squared. And so if it's proportional to speed squared, if you double the speed, you'd have 2 times 2, and it's 4 times the kinetic energy if you double the speed. So that's why this question is here, to contrast to a future one. Now, impulse is a word I actually don't like to use. Impulse is equal to change in momentum. And I'm like, I can write change in momentum. I don't need a new word for it. What's the mathematical symbol we use that means change in? We use a delta. Delta always means the change in. It means the final amount minus the initial amount. And so impulse, I missed the U, is equal to delta P, change in momentum. The reason the textbook and many textbooks use impulse is because they define impulse as one side of an equation. If we take Newton's second law, so far you've learned Newton's second law is sum of the forces equals mass times acceleration, or force net equals mass times acceleration, right? That's what you've seen for Newton's second law, right? Now that's a vector equation, so I should have vector signs if I want to be complete. But then we have the definition of acceleration. Tell me what acceleration just means, and then we'll go to the definition. What does it mean if you're accelerating?
You're speeding up.
Okay, you're changing velocity, which could be speeding up, could be slowing down, could be changing direction. Right, so in your car, if you press on the accelerator, you accelerate. If you press on the brake, you accelerate. If you turn the steering wheel, you accelerate. It would confuse most people because most people think the answer that you gave, the acceleration is speeding up. But technically, it's a change in velocity divided by a change in time. And so if I take this acceleration and say, well, it's the change in velocity over the change in time, then I can rewrite Newton's second law to say the net force is mass times change in velocity over change in time. But as long as the mass of the object isn't changing, I can extend that delta outside of the mass. If the mass is constant, then the change in mass is zero. So change in mass times velocity is just mass times change in velocity. But what is that that's inside the parenthesis? Mass times velocity, what's that equal to? The topic of the day. Momentum, yeah. That's equal to momentum. So Newton's second law is correctly written and just for your enjoyment, this is the correct form of Newton's second law. Actually, the truly correct form is as a derivative. It's a calculus equation. But that derivative means change in momentum over change in time. So this is the correct definition of Newton's second law. The one that we've learned and worked with is correct if mass is unchanging. So this one's always correct. And that thing I said, if the mass is constant, that was how we got to the version that we've been using. So that version we've been using only is correct if we don't have mass changing, which is usually the case. So now with this Newton's second law, I'm just going to multiply both sides of the equation in the box by delta t. But of course, what's delta t divided by delta t? It cancels out. Now I wrote as cancel out. I have the power of the eraser. I'm going to erase it to make it so it looks cleaner. So force net multiplied by change in time is equal to change in momentum. Now I've gone through a lot of math to get to a point, and that's the point that starts this page. Impulse is defined as the product of force times the time over which that force is acting. It called it here the contact time. But by Newton's second law, the force times the contact time is equal to the change in momentum. So the impulse is the left side of that equation. So impulse equals change in momentum. That's the reason the textbook uses impulse, is because we separate the force causing change in momentum from the change in momentum. So this is actually really important. Have a picture of a car here. Can the man get the car moving? Well, of course, as long as it's on level ground. You can get it moving. Is he going to get moving fast? It depends on how long he pushes. He can push with a certain force as long as that force is bigger than the force of rolling friction. Rolling friction is it's a measurement that tells us about how much energy is taken away by the tires. Actually, they compress as they roll, right? Your tire it's not a circle. It's flat on the side, it's touching the ground. And furthermore, they're made so that they will deform a little, so they grip the ground. And there's a little bit of energy lost in that. And that's the energy that's what the rolling friction is. But as long as his force is bigger than that, it will accelerate as long as he keeps pushing. And so the momentum will get bigger and bigger and bigger as long as he keeps pushing with the force bigger than that rolling friction. And so the longer he pushes, the faster it goes, until either he tires out, most likely occurrence, or he reaches the point where the rolling friction is equal to his force, or he can't go any faster. Yeah, I just went through this. Now, taking that relation and applying it to something simple, a car crash. That's reasonably simple. Notice the first one shows a truck hitting a stack of hay. The stack of hay does not apply a very big force to the truck. And because it doesn't apply a very big force to the truck, and the truck's not in the hay all that long, it's not a very big impulse, not a very big change in momentum, so it doesn't slow down a lot. Of course, there could be something hidden in that haystack. Have you guys seen the picture this week of the people who built the nice big snowman in Petersburg, Kentucky?
Yeah.
And some joker with a four-wheel drive vehicle thought it'd be funny to run over their big snowman, but they built it on the stump of a tree.
That's awesome.
Yeah, you wish it did more damage so the truck couldn't drive away. The truck drove away, so all they have is a picture of, the fender of the truck in the snow. But yeah, so just have to point out it's possible there could be something in here that would be more significant. But because this didn't supply very big force, it didn't slow it down. Now, if you had a big enough haystack, you'd have enough time to slow it down. You come with the same momentum and you hit El Capitan, biggest granitic monolith. That thing there, it don't move. And so the momentum change for this truck is going to be really big. Its entire mass size velocity is down to 0. And the time is going to be very short. Because it's a short time, it's going to be a really big force. So this plays into very practical things. I have pictures here of airbags in a car. And I just like to go through the history of safety in an automobile. So originally, you didn't have seat belts, right? I mean, I still remember as a kid, we would just lie down in the window well of the car while it's driving to sleep and stuff like that. We weren't all that concerned. Then they came out with shoulders or seat belts. Now, when you get in an accident, what is the seat belt going to do? Cut you in half. Good answer. Especially if you're driving a Yugo. Yugos are cars that came out when I was in college. Yugoslavia was trying to get into the car business in the United States, and they made a one-size-fits-all. And I'm not kidding you, one-size-fits-all. The seats didn't even move. You just got in, and if you're tall, well, less comfort for you. If you're short, well, good luck reaching the pedals. And the Yugos had seat belts because law required it, but their seat belts were the worst. The first kind of seat belt made, where you have a bolt that bolts one side of the seat belt here, and a bolt that bolts the clasp over here, and then you just pull the seat belt across, you adjust the tension, you drive, and if you hit something, the seatbelt doesn't give, and it does what Amber said. Basically, tries to cut you in half. You have a really big force there in your midsection, and your upper body, just like your lower body, has a mass and it has a velocity, so it has momentum. And so if you hit something and your waist doesn't move, what's going to happen to your upper body? You have a pivot point that's going to go whammo. And so it's just going to make your head hit the steering wheel harder. Good safety feature, right? Yeah.
Why is it that on airplanes that they still have seatbelts that are like that?
Well, they're not like that anymore. They look like that, but they're not. So I'm going to talk about the differences. So the next advance then is the shoulder strap. The shoulder strap now comes across your chest, so when you stop, your chest stops as well and you don't go flying forward. Much better. But you probably have seen people with terrible bruises from the shoulder strap. But general rule, we'll take bad bruises over crushing our face into the steering wheel. But then we have advances. So seatbelts today are not bolted in like I described with Yugo. You have a tensioner, a spring, if you will, that goes from the chassis to the seatbelt mechanism. So if you get in a crash, now the seatbelts also, these days, okay, you guys don't even know this, but the old school seatbelts were like you have in an airplane, where you attach it and then you adjust it to make it so it's tight on you. These days, they have the spring-loaded thing, and you bring it out, and have you ever noticed you pull it too fast and it gets stuck, and you have to bring it all the way back and get really frustrating, right? I mean, they've made a lot of advances. That's because they want the seatbelt to allow you to move freely unless you get in an accident. So if it starts pulling too fast, then it locks because it says, uh-oh, the car's stopping fast, we need to hold the person in place. And so then that mechanism will lock, and then you pull against that spring. You pull against the spring because it's going to stretch out the time it takes for you to stop. And if you stretch out the time, what's that going to do to the force? I better write the equation up here again. If you stretch out the time, what does that do to the force?
It makes it smaller.
Makes it smaller because you have the same change in momentum. You're going from whatever your initial speed was to stopped. And the change in momentum, I'm going to write it without the vectors here, is force net delta T. So having that spring to make it take longer is going to lower the force. And so you have that on both the shoulder strap and, well, it's actually on the edge there that's tied to both the shoulder strap and the seatbelt. So the whole thing moves forward a little bit to give you more time and thus cause less damage. And then you have the latest and greatest advance. The latest and greatest advance is the airbag. Now, notice my picture up there on the left. Your car senses that you're in a crash. How does it sense that? It has sensors like on the bumper. If the bumper gets a shock big enough, it says, ooh, collision alert. Hence that viral video of the lady very slowly shuffling across the road. This guy in the car gets frustrated and honks the horn, and she bangs the bumper with her purse, and his airbag goes off.
Wait, that actually happened, or was it staged?
It could have been staged, who knows? But it's funny, okay? And it could happen, that's the key. Like the Jimmy Kimmel one where this girl was doing a little dance and she falls over the table and the camel catches fire. Anyway, everybody thought that was real for like a month. I found out, nope, that was from Jimmy Kimmel stunts. So you have a sensor that says the car has hit something or it's accelerating too hard. And these days it's very complex. You have like a Mercedes-Benz, which I don't, you have something like 21 different airbags. And it detects which direction the acceleration is, and it's only going to use the appropriate airbags for the type of directional impact. So you have the impact airbag. The airbag has an explosive. It's like ammonium hydroxide or something like that. It has an explosive there, and so it goes kablooey. And that explosion makes it come flying out at you. How fast do you suppose the airbag is coming at you? How fast?
61.
Way faster. 200 miles an hour. Does it say that up there? Or do you know?
No, I guess.
It's coming at you at about 200 miles an hour.
Isn't it going to do more harm than anything?
If it hits you at that speed, it can. And for that reason, people who are really short, it's actually a little dangerous. And so for short people, it's my understanding of federal law, you could go into the dealership and have them disable the airbags because you're short and it's a safety hazard to you. Because yeah, if that hits you at 200 miles an hour and you're a little person, it can cause a lot of damage. Don't have a child sitting in the front seat. And that's one thing, they get hit by that airbag, it's going to be painful to them. Okay, so the goal is this bag blows up and it completely inflates before you touch it. So you're coming toward it, it's flying toward you at 200 miles an hour, right? You got 250 miles an hour relative speed. You want it to stop before you hit it. On the back of those bags, you have big holes. So they instantly deflate. And so it's like hitting a pillow that's soft because it's going to deflate quickly as well. Question?
Do the side airbags go out that fast too?
I imagine they do because they want them to get out there before you hit them, right? You have, let's say it's the window airbag. You have airbags that will come down and drape the window so glass doesn't hit you, you don't hit glass. And so it's a softer collision there, but it's got to get down there before you get over there or it's too late. So high speed is important for these. Do you have a question, Grace?
Oh, no, I was just starting.
Interesting.
So what's the entire point of the airbag?
To protect you
Okay, to protect you, how?
by putting a bunch of force.
Okay, it makes the time that you slow down longer. Your car stops quickly, and we want to make you stop more slowly than your car. And if we make you stop more slowly, that's going to make a longer delta T and hence a smaller net force acting on you. So it's lowering the force acting on your body. So these airbags are really great safety devices in our car. It's just they deploy really fast. And they have these dangerous explosives that make not happy gases. I know this shows nitrogen gas, but I believe there's some other things that you don't want to hang out with. Okay, so a question for you. A fast-moving car hitting a haystack or hitting a cement wall produces vastly different results. Which is the same? So let's just go through these one by one because you notice you have options of and. So if you're in the car that's moving fast and you hit a haystack and come to a stop, so in both cases, come to a stop. It's just going to take a lot longer for the haystack. So how does the momentum change for your body compare in the two cases? It's the same because you start with the same momentum and you end with the same momentum of 0. So they both have the same change in momentum. What about impulse?
Same.
Why do you say impulse is the same?
Because impulse is the change in momentum, and if they have the same change in momentum.
Exactly. It means the change in momentum, so it's the same thing.
So the answer is B.
What about the force?
It's not the same force.
Not the same force. That's the whole goal of the airbags. You extend the time, so you lower the force. So the answer was D, A and B. Everybody understand those concepts?
Yes.
I like the affirmative. Okay, now conservation of momentum. With that equation, the Newton's second law equation that says the net force multiplied by the change in time is equal to the change in momentum. In the special case, not the every case, but the special case, where the net force is 0, then what would the change in momentum be? Let's say we take this ball. If the net force acting on the ball is 0, what's the change in momentum of the ball?
0.
0, right. So if the net force is 0, the change in momentum is 0. In that case, momentum stays constant. We call that in physics conserved. So momentum is conserved if the net force on an object is 0. So if I take this ball and let go, is momentum going to be conserved for the ball? Okay, I got a definite answer from Hannah. No, she's correct. It won't be conserved. Its momentum is going to increase in downward direction. Why did the momentum not stay 0?
Because the velocity changed.
Okay, but what made it change?
External force.
An external force, right. The net force on this was not 0. It had, when I let go, it had force of gravity down and virtually no upward force. So momentum wasn't conserved with this ball. But if you have a system with two interactions, or two things interacting, like let's take an example of, let us say that, Richard and some random person we'll call Nalgo are on ice skates. And with those ice skates, if we keep our ice skates straight ahead, we have very low friction. And so if we take the system of Richard and Nalgo, even if they hit each other, the external force on the system of Richard and Nalgo is going to be 0. Right? If I hit her, there's going to be a force of her acting on me, but Newton's third law says there's going to be an equal and opposite force of me acting on her. So if we take the sum of the forces on our bodies, now we have the upward and downward forces that are going to add up to 0. And horizontally, there's no external force, it's only the internal force. And so in the system of the two interacting bodies, momentum should be conserved. As long as we're on our ice skates with them straight so there's no friction. So I wanted to show this off to my then girlfriend Nalco. So we go to Riverfront Park in Spokane, and we're ice skating there. And I said, hey, check this out. And I tell her, now I'm going to push you, and then we'll see how each of us move. Because Nalka was not young. She was young, so was I. She was a short girl. She was like 5'2" or something. Came up to my armpit, and so her mass was well less than mine, and so she should move, about twice as fast as I did according to this equation. And so I pushed her, keeping her skates straight and everything. And what happened? She fell. I told her I was going to push her in the whole 9 yards. She fell. She cried. It was a bad day. It got even worse when I took my skates off. I took my skate off and my right foot was covered in blood. I was like, oh, what happened? So I take off my sock. My foot's fine. It was somebody else's blood in the skate.
Ew.
Yeah. That was nasty. Anyway, so just a warning I learned from this. Demonstrating conservation of momentum with friends is not always good, especially if it's with your significant other, because it made a nice romantic ice skating date into a crying affair. But it was still good in concept. Momentum should have been conserved. She should have been going about twice as fast as me. So we could take an example. There's Richard. There's Nalko. Initially, our speeds were velocity of Richard. I'll put a little I for initial equals 0. And velocity of Nalko, initial, equals 0. And then we have the force. So I push on her with the force of Richard on Nalko. And if I push on Nalko with that force, what's going to happen as far as Nalko pushing on Richard? Let's say I push with a force of 5 newtons. How hard is she going to push on me?
5 newtons.
5 newtons. What's her direction going to be? Opposite direction. So there's also the force of Nalko on Richard that's equal. So the sum of the forces in the x direction is 0. That's supposed to be a sigma. I know you guys aren't used to enough that being sloppy is going to work. The sum of the force in the x direction is 0. After the push, let us suppose that the speed of Richard final is equal to minus 2 meters per second. And say mass of Richard is equal to 100 kilograms. Mass of Nalko is equal to 50 kilograms. That's actually more than she had in mass. She was small. How fast is Nalko's final speed going to be?
She falls over.
Assuming everything worked as planned, that there's no friction, that she does not fall. How can I calculate how fast she would be going?
Wait, you're going back how fast?
I started at 0 and I then end up at minus 2 meters per second.
And then
She starts at 0. Her mass is 1/2 of my mass.
how then she would go forward 4 meters.
Okay. Bryson put it together logically because her mass is half as big. Her speed's going to have to be twice as big so that it comes out to the same. If you do it mathematically, you have momentum initial is equal to mass of Richard times velocity of Richard initial plus mass of Nalko times the velocity of Nalko initial, which was 0 because we both start at rest. And momentum final is equal to mass of Richard, velocity of Richard final, plus mass of Nalko, velocity of Nalko final. And then for conservation of momentum, momentum initial equals momentum final. So that means 0 is equal to mass of Richard, velocity of Richard final, plus mass of Nalko or velocity of Nalko final. And if I want to find the velocity of null final, well, we just solve for v null final. So math steps, subtract mass of Richard, velocity of Richard final from both sides. And I end up with, and I've run out of space pretty much, minus mass Richard, velocity of Richard final equals mass null, velocity of null final. Final step before putting in numbers, I want to get the velocity of null by herself. So I have to divide by it. And I end up with, now these cancel, velocity of null final is equal to minus mass of Richard over mass of null, velocity of Richard final. And now we can see exactly what Bryson did in his head. Mass of Richard is 100, mass of null is 50, so 100 divided by 50 is, it's 2. We had a minus sign here, so minus 2 times minus 2 meters per second gives me plus 4 meters per second. The plus versus minus indicates direction.
So, okay, so the plus versus minus indicates direction. So
Yeah.
do you want us to use that on the homework? Because on the first homework, I didn't use the plus. I don't think I used the plus or minus indicating direction. Because you didn't teach us that.
From now on, yes.
Okay. Okay, good to know.
Yeah, good to know. I would have to look to see where that was an issue, but
So minus would just be going backward.
yeah, minus would be going backwards.
Well, on the homework of the ball falling. So it's like going up
So the
and then
ball-
coming down.
Mhm.
It would have been minus coming down.
The velocity would be minus.
Yeah.
And the acceleration will always be minus.
And the reason minus was to the left here is because I defined plus to the right.
So we have to define it if it's right or left.
Yeah, it's always important to define directions. And our convention is pluses to the right and pluses up. But that's just a convention. If you define differently, you work it differently. Okay, 2 types of collisions. Actually, yeah, 2 types of collisions. I want to talk about one kind of collision before I do this. Let's say that I have a ship that's traveling along at 20 knots, 20 nautical miles per hour. And that ship suddenly strikes a big glob of tar that was initially at rest. Well, it strikes that glob of tar is going to stick to the ship. And so what's going to happen to the ship's speed when it strikes that glob of tar?
Slow down.
It's going to slow down. Why is it going to slow down?
There's more mass.
Okay, what you have to
It's something
do,
at rest. But I mean, they're in water, so the tar's gonna start moving with it. But because it hit a bigger mass, it's gonna slow.
right, what you have to do is you have to take the masses and the velocities, and you had initially the ship has this mass and velocity, so this momentum. The tar has this mass and 0 velocity because it was just sitting there. And so that total momentum is going to be the momentum of the ship and the tar after they collide. And so you add them together and divide by the total mass, and you get the new speed. Now, do keep in mind that in water, there's a lot of external resistance, right? The water resistance, ships don't just keep going constant speed unless they keep the screw running. But during the collision, remember we had the change in momentum was the force net multiplied by the time. If the interaction time is really small, then during the collision, you'll still have momentum conserved. So during the collision, momentum will be conserved. After, maybe not. Before, maybe not. We use the same thing in car collisions. If we have 2 cars collide, when the police get there, they get out their little wheel and they measure the skid marks. And they measure those skid marks because you know what the coefficient of friction is between the tires and the road. And if you know the distance and you know the mass of the car, you can calculate how much energy it lost, something that is in the end of this chapter, and thus you can determine how much the speed changed while it was skidding.
And then they can determine how fast the car was going.
And then they measure how far the skids were after, and then they work their way back. They say, okay, ended up here, skidded this far, and so this is how fast it was moving just after the collision. During the collision, they say momentum was conserved, and calculate how fast that it was going before, or just before the collision. Then they go back the rest of the skid marks and say how fast they were traveling before they saw there was a hazard and locked up the brakes.
See, that's why I was always wondering when they would talk about crash scene, they were like, and the car was going this. I'm like, how do you know how fast the car was going? Math.
Yeah, math and physics. So we have two fundamental types of collision. The first type of collision I talked about is when they stick together. If they stick together, we call that an inelastic collision. And there's completely inelastic, partially inelastic. As far as we're concerned, inelastic simply means they stick together. Right? You can look at other places and they'll say completely inelastic. That's the technical term we need to use for it. But we'll just say that. They stick together and they actually are going to have energy that's converted into something else. The other kind is called inelastic. Okay, what did I say that was called?
Inelastic.
Okay, good. The other kind is called elastic, what it says up here. And an elastic collision is when two things bounce off of each other and no energy is lost. I hate talking about energy when we haven't even defined it yet. But those are the two types of collisions. So if it's elastic, they bounce and don't lose energy. An example would be if I let go of this ball and it bounced elastically off the floor, it would come back up to my hand. Clearly, it wasn't very elastic. Also, I clearly am not good at kicking the ball to myself. It also wasn't completely inelastic, because if it had been completely inelastic, it would just stay on the ground and not bounce back. So it was somewhere in between. There was a question here? Jessica?
Inelastic, can you give me a definition again?
Inelastic was they stick together.
So, but what if you dropped a golf ball, it would bounce?
Yeah, if you drop a golf ball, it will bounce almost all the way back up.
Yeah, is that because it's not losing that much?
It's not losing very much energy. I mean, you want your golf ball to lose energy when you hit it. Well, you transfer energy from your club face to the ball, but you want it to be very bouncy. And so we talk about things like coefficient of restitution, how much energy is returned. So for the golf ball, they're shooting for a coefficient of restitution of 1. It's not quite that. If you watch high-speed photographs of a golf ball being hit by a club, those golf balls get smashed down to less than half of their initial width.
Really?
Well, yeah. If you're not big, if you're actually a good golfer, those golf balls compress a lot, which is shocking because they're pretty hard. And you tend to think they might break, but they don't.
What was the other definition?
Okay, so elastic is they bounce, right?
Yeah.
And what we mean when we say elastic here is completely.
Inelastic when they stick.
And then inelastic, they stick together. So we're going to, in lab next week, I believe we're going to be doing some things with collisions. And we'll look at elastic collisions versus inelastic collisions to observe what happens with energy and whatnot. Notice we have an example here with numbers. Two identical cars, so they have the same mass. One has a mass of, or a speed of 10, let's say miles per hour, right? Because you have to have units. Just having it without units is useless. The other one is initially at rest. They collide and stick together, and then they have a final speed that's going to be 10 times m plus 0 times m, divided by the total mass. What's the total mass of the two cars?
You didn't give us the mass of the cars.
Yes, but we can put it in terms of m.
It is 2.
2m. So we'd have 10m plus 0 over 2m gives me 5m. By the way, on one of the homework assignments, somebody said 10 divided by 2 is 10. I know that you know better than that math. I don't remember who it is, just so nobody worries about it. You know, that I don't remember who, well, actually, not even don't remember. When you're grading them, you don't know who it is. The way we grade them, you just see their answer and don't know whose paper you're grading. Anyway, so you'd have a final speed of 5 miles per hour if they bounce off, or if they stick together. If they bounce off of each other, the calculations are more complicated. And for this class, we're not going to do those calculations. But if they are the same mass, when they bounce off each other, they just exchange velocities. And so if these were the same mass, and they bounced off of each other, then the orange one would stop and the green one would take off at 10 miles per hour. And if you had like this one's 10 miles per hour and this one's coming at it at 5 miles per hour, if they bounce off each other, what would you have? Right. The orange one would go off at 5 miles per hour to the left, and the green one would go off 10 miles per hour to the right. That's exactly what the point of those are. Those are little physics desk toy to illustrate how this works. And so, yeah, if you take, well, it's a little more complicated because if you take 2 balls and you hit, 2 balls will come off the other side.
Yeah.
The reason for that is actually tricky. You have all these balls, and if you have 2 balls that hit it, technically, this one hits first. And it takes time for the shock wave to go through that first ball so the second ball even knows there's a collision. And while that's going on, the shock wave is going this way through this ball. And then when the shock wave gets to here, you get a return shock wave. And so you have those 2 shock waves going through, the blue one ahead of the red one. And so the blue one takes this one off, and the red one takes this one off. I studied shock physics for my master's work, so I got a lot of training in that area. It's very cool, because you're like, wow, so I can have 3 coming down on one side and 2 on the other side. They hit, and then it has 2 come off and 3 in the opposite sides. And yeah, because it's the shock waves that are making that happen. Okay, we have 3 minutes to introduce work. Now, just for your sanity's sake, you know how long it takes us to get to this point in general physics? Yeah, like a month and a half or so. And here we've gotten there in 2 weeks. Obviously, we can't have all of the depth and all of the problem-solving abilities and learning that we have in that class. Because how would you learn that quickly? Right, so the depth of this class is not as deep because we're covering stuff really quickly, and we want you to have a passing knowledge, and I emphasize the word passing because that first quiz wasn't passing. A passing knowledge of these physics ideas. And even more so, I really want you to understand the scientific method through which all of the science we're learning throughout the semester is derived. It all comes from people observing something interesting and then saying, why? I wonder why. That's the essence of being a scientist. Developing a hypothesis that's based on scientific ideas that explains why the thing they observed happened and makes testable predictions, and then testing. So when we start talking about work, it's actually a relatively recent understanding of man that there is a difference between momentum and energy. And so I talk about work, you're like, wait, work and energy are very tightly related. So we're only going to talk about work in the next minute. Work is the result of, as you see in red, a force acting on an object over a distance. Right now, there's this string. There's a force of gravity acting on it. There's a force normal acting on it. But there's no motion for it. Hence, there's no work being done here because there's no motion. Now, if I take this and put it on my hand and I lift it, if my motion is parallel to the force, there's a work. If it's perpendicular, there's still no work. So if I take this and move it horizontally, there's no work because the force is perpendicular to the distance it moves.
So it can only be vertical?
Well, because gravity is vertical, gravity can only do work if it moves vertically. Yeah, so if I go like this and push with my finger, I have a force this way from my finger and motion that way, so I'm doing work. There's a force of friction in this direction. That's opposite. That's doing negative work. And that's where we'll end the week. Have a great weekend. Enjoy your day off on Sunday or Monday. Yeah, everybody gets Sunday off. Enjoy Monday. It is Martin Luther King Jr. holiday. Take a few moments to think about how race relations have changed and improved, a lot more freedom. A lot of it brought about by people like Martin Luther King Jr.